Hey guys, well in my last video I showed you how to deal with solving an nth order linear constant coefficient homogeneous differential equation, and I discussed the two main issues, which are repeated roots and complex roots to the auxiliary equation for that differential equation. So I want to do an example here to just practice. I want to do maybe one or two examples just to practice what I went through in the last video. So the first one is just d squared plus 4 quantity squared times d plus 1 cubed of y equals 0. So of course my auxiliary equation here is just r squared plus 4 quantity squared times r plus 1 cubed equals 0. And the roots of this, see, it's already factored pretty much, right? The roots of this are pretty easy to get. You have negative 1, negative 1, negative 1. You should write down whenever a root shows up multiple times, you need to write it down multiple times. So there's a power of 3 on that r plus 1 factor. And then on the r squared plus 4, we can use the quadratic formula if we're not sure how it factors, but I think everybody will probably agree with me that the roots are going to be plus and minus 2i twice. Okay? So we have some repeat roots here. But actually, once we have the roots written down, we can immediately go and write down the solution to this problem, right? So I can actually already start writing down what y of x is. Okay? So the first root is negative 1, so we know that the first term of my solution will be c1 e to the negative x. Now, that negative 1 repeats. So if it repeats, then I can put down a second term where I add an extra x into the expression. So we get c2x e to the negative x. And then the next term would just be, again, another repeat of that same root. So now I'm going to write x squared e to the negative x. Okay, and now I have the imaginary roots. The roots plus and minus 2i, let's see, so when I think about a plus or minus bi, right, for the plus or minus 2i, a is 0 and the b is 2. So remember that the solutions are going to be e to the ax times the sine or cosine of bx. In this case, there is no exponential part. The a is 0. So all we're going to get c4, and we're just simply going to get cosine of 2x, right? And then we're going to get c5 with sine of 2x. Okay? And then we're just going to keep going because we have the plus or minus 2i again. And remember that, as I said, what we have to do for that is tack on an extra x into the solution. So we'll end up getting c6 times x cosine of x, and then c7 x sine of 2x. It's really pretty straightforward, okay? As long as you can get these roots to begin with, and as long as you know how to handle repeats and complex numbers, yeah, you're actually spending more time writing down the answer than you are actually solving the problem, okay? Hope that makes sense. You should let me know if it doesn't. I can certainly go through it with you a little bit more. Let me do one more example just to really make sure that we're good with this. Okay, let's do one more. Okay, so let's do this one. Let's solve the following equation. Let's do d squared minus 6d plus 13 quantity squared of y equals 0. Okay? On this one, the auxiliary equation, of course, is just r squared minus 6r plus 13 squared equals 0. So you just change all the d's to r's. This quadratic does not factor nicely, so, well, that's okay. We can just use the quadratic formula to get the roots. So if we do that, we're going to get, 6 plus or minus the square root of 36 minus 4 times 13, which is 52, all over 2. And that would be 3 plus or minus, let's see, the square root of 36 minus 52, that would be negative 16. The square root of negative 16 is 4i. I divide that by 2 and I get 2i. And I need to remember that that root is repeating twice. That root is repeating twice. This is a differential equation of order 4. So I'm going to get 4 terms in my final answer down here. So I actually should probably write down this root twice. Whenever the root repeats, it's good to write it down. Same way that we would normally do for the eigenvalues of a matrix. If they repeat, we tend to write the roots down multiple times. So let me just go ahead and show you here how this is going to look. So y of x equals, we're going to have c1 e to the 3x cosine of 2x, right? The 3 and the 2 are coming from the complex number, the real and imaginary parts. And then there's a companion term, which is c2 e to the 3x times the sine of 2x. Okay, and then 2 more terms which are the same as these, but with x's stacked in front. So c3x e to the 3x cosine of 2x, right? And then finally, c4x e, I'm sorry, that's an e to the 3x sine of 2x. Like that. I hope that's readable. So there you go. That right there is the answer. See, it does not take very long to derive the solution. You do less work up here than it takes to actually just write down the answer. So it goes pretty quickly. Again, it all hinges on being able to factor the auxiliary equation. Of course, when I give you problems, I'm going to make sure that they are doable in that sense. I might factor them for you, like you've seen in some of the earlier examples. Or there'll be something that you can use a quadratic equation for, or where you can, I don't know, factor by grouping, or whatever the case may be. But this is the whole idea behind solving nth-order linear constant coefficient differential equations. This is section 8.2. I hope this all makes sense. I'd like you to absorb this stuff. Try the problems that I'm asking you to do from 8.2, and let me know if you have any questions. I hope that this has been a helpful video, and I look forward to seeing you again very soon. Thanks a lot. Take care.